This lesson we're going to be discussing continuity. In previous lessons we have looked at continuity, but today we're going to give it a more formal definition. Most of the techniques that we use in calculus require that functions be continuous. A function is continuous if you draw it in one motion without picking up your pencil. That's how we described continuity earlier. But now let's look at it more mathematically. A function is continuous at a point if the limit is the same as the value of the function. Notice with the example here, this function has discontinuities at x equals 1 and x equals 2. Our definition says that a function is continuous at a point if the limit is the same. So let's look at the limit of f of x as x approaches some value a has to be equal to f of a in order for this function to be continuous. So on some slides that we're going to be looking at, we'll actually go through this process of determining if a function is continuous or discontinuous at a point. There are three criteria that must be met in order for a function to be continuous at any point A. Here's the graph of a function, and let's look at the three criteria. First of all, f of a must be defined in order for this function to be continuous. Second, the limit of the function as x approaches a must exist. And then third, the limit of the function as x approaches a has to equal f of a. If all three of those criteria are met, then this function is continuous at that point a. Now we have some endpoints on this graph. You might be thinking, well, part 2 says the limit of f of x as x approaches a has to exist. And in order for us to show a limit exists, we have to show the one-sided limits exist. But we don't have, at x equals 4, we can't approach 4 from the right. However, we can use one-sided limits to show that it is continuous at an endpoint. So it is continuous at x equals 0 and x equals 4 because the one-sided limits match the value of the function. Let's look at a graph. Here are our three criteria. We have to show these three criteria are met if a function is continuous at a particular point. Looking at the graph, let's look at it from left to right. Where is the first value of x that you may think this function is not continuous? We would probably say at x equals 1. So let's apply the three criteria and see if this function is continuous at x equals 1. So number 1, it said f of a is defined. Well, the value we're checking is x equals 1, so we are going to look at f of 1. And if we look at the graph right here, the function is not defined at 1. So we can stop and we can say this function is not continuous at x equals 1. We're finished. The next point we may want to check appears to be at x equals 1.5. So at x equals 1.5, let's go through the three criteria. We would have 1 is f of 1.5 defined. We can see here that it is defined at -1. So this equals -1. So we move to the next criteria. Does the limit of f of x as x approaches 1.5 exist? We know we have to show the one-sided limits equal each other in order for this limit to exist. So let's look at the one-sided limits. We would have the limit of f of x as x approaches 1.5 from the left, and looking at the graph, as x approaches 1.5 from the left, it equals -1. So let's look at the other one-sided limit, the limit of f of x as x approaches 1.5 from the right. So if we look at as x approaches 1.5 from the right, we can see the function is approaching 2. So we've shown this limit does not exist. Therefore, this function is not continuous at x equals 1.5. The last point where it appears it may be discontinuous is at x equals 3. So here are the three criteria we need to show. So we're going to check x equals 3. So first criteria, f of 3, is that defined? Well, if we look at the graph, we can see it is defined up here. So f of 3 equals 4. So we move on to criteria number 2. Does the limit of f of x as x approaches 3, does this exist? We're going to look at our one-sided limits. I'm going to do the work up here to give us more room. So we would look at the limit of f of x as x approaches 3 from the left. And as we approach 3 from the left, we can see the y values are approaching. We'll estimate that to be maybe 1.4. Let's look at the limit of f of x as x approaches 3 from the right. So as x approaches 3 from the right, looking at the y values, they are approaching 1.4 also. So this limit does exist, and it equals 1.4. So we move on to the third criteria. Does f of 3 equal the limit of f of x as x approaches 3? Well, we can see f of 3 equals 4, but the limit of f of x as x approaches 3 equals 1.4, so they do not equal each other. Therefore, this is not continuous at x equals 3. Where's the following functions discontinuous? So we have the greatest integer function. We've seen the greatest integer function previously. Let's look at the graph. With the greatest integer function, we know the function, let's take x equals 3. We know the function is defined here and not here. So let's look at our three criteria. First, f of 3, is that defined? Yes, that equals 3. So we go to the next criteria. The limit of f of x as x approaches 3. So we're going to look at our one-sided limits. The limit of f of x as x approaches 3 from the left, we can see that equals 2. The limit of f of x as x approaches 3 from the right, we see that equals 3. So criteria 2 does not hold. This is not continuous at x equals 3. And you notice the same thing would happen for every integer value. So this would not be continuous at any integer value. Where is the following function discontinuous? Looking at this function, we would probably say where the denominator equals 0, which would be x equals 2, this function would be discontinuous. Well, we need to show this using our three criteria. So 1, is f of 2 defined? Well, we can see if we plug 2 into the function, we'd get 4 minus 2 minus 2, and so that would all be over 0. So this is going to be undefined. So this fails criteria number 1. So at x equals 2, this is discontinuous. Here we have a piecewise function. Where is this function discontinuous? If we are to graph this function, it would look something like this. 1 over x squared would look something like this. Now we can see this function is not, it does not have a value when x equals 0. But this piecewise function gives it a value when x equals 0. It says y equals 1. So let's take a look at our three criteria. So first, f of 0. That does exist. That's defined at 1. So we move to the next criteria. The limit of f of x as x approaches 0 from the left. I'm sorry, we're just going to state, does the limit of f of x as x approaches 0 exist? And then we will look at the one-sided limits. So let's take away the from the left. So in order to determine if this limit exists, we're going to look at the one-sided limits. So we would have the limit of f of x as x approaches 0 from the left. We can see that goes off to infinity. Now we could stop right there and say this limit does not exist. Therefore, number 2 is not met. But I'm just going to write the second piece. This would be the limit of f of x as x approaches 0 from the right. That does equal infinity also, but that doesn't mean the limit exists. We could write for number 2 infinity, but we know that this limit does not exist. Therefore, it is not continuous at x equals 0. Where is the following function discontinuous? We have another piecewise function. Now, if we were to simplify this function, it appears that x squared minus x minus 2 over x minus 2, the numerator could be factored, x minus 2, x plus 1, all over x minus 2, and we could reduce the x minus 2's. So x plus 1 is equivalent to x squared minus x minus 2 divided by x minus 2, except at 2. Because notice, here, if we plugged in the value 2, we get 0 in the denominator, so it's undefined. But if we plugged in 2 for this, we would get 3. So if we were to graph the original function, x squared minus x minus 2 divided by x minus 2, it would look like the straight line x plus 1, but it would not be defined at 2. So if I try to draw that in, I have a y-intercept of 1 and a slope of 1. And then I'll try to stop at 2 and make it undefined. So that's what the function would look like. However, this is defined at x equals 2. It says if x equals 2, y equals 1. So let's see if this is continuous or not continuous, because it appears that this would be the value down here where the function is defined and not up here where the open circle is. But let's go through this process. First off, we would look at f of 2. That equals 1. Second, we would look at the limit of f of x as x approaches 2 and see if that exists. So we're going to look at our one-sided limits, the limit of f of x as x approaches 2 from the left. Now as x approaches 2 from the left, we are going to approach 2 from the left here, and notice we would be approaching 3. The limit of f of x as x approaches 3 from the right, and we could look at our graph again, and we see that we're approaching 3. Therefore, this limit does exist, and it equals 3. So we move to criteria number 3. Does f of 2 equal the limit of f of x as x approaches 3? And if we look back at number 1 and 2 criteria, we see those do not equal each other. Therefore, these are not equivalent. Therefore, this piecewise function is not continuous at x equals 2. Now there are several different kinds of discontinuities. What we just looked at is one type of discontinuity. Here, this example that I'm showing you is called a removable discontinuity. A removable discontinuity occurs when a point is just taken from the graph to make it discontinuous. Another way to think about it is if I replaced this point right here, would it now be continuous? And in this case, yes, it would be. So this is considered a removable discontinuity. Since I could plug that point back in and now it's continuous, it's called a removable discontinuity. Here's some examples of other types of discontinuities. Here, this is called a jump discontinuity, and you can see the reason why it's called a jump. To complete the graph, we have to jump up to complete it. Another type of discontinuity is when a value has an asymptote at that value, and so it's called an infinite discontinuity. And we looked at this graph earlier, and we saw this graph is just oscillating infinitely close to x equals 0 from both sides. This is called an oscillating discontinuity. Removing a discontinuity. Here we have a function x cubed minus 1 all over x squared minus 1. We can see that there is a discontinuity at x equals 1. If we plugged in 1 for x, the denominator would equal 0. We're going to try to write an extended function that is continuous at x equals 1. So the idea is we're going to write a piecewise function to try to make it defined at that point. So it's a removable discontinuity. We're going to plug that point back in to make it continuous at x equals 1. So let's take a look at the limit of x cubed minus 1 divided by x squared minus 1 as x approaches 1. If we use direct substitution, do you notice we would get 0 divided by 0, the indeterminate form? Well, since we got the indeterminate form, we're going to try to manipulate that expression so we can use direct substitution. So if we factor the numerator and factor the denominator, you can see that we can reduce one of the factors, x minus 1 and x minus 1. So we can reduce those. Now, what's important to understand here is that is the reason why we got the indeterminate form 0 over 0. We had the same factor in the numerator as in the denominator. That gives us our 0 divided by 0, the indeterminate form. That indicates we're going to have a removable discontinuity. A point is just taken from the graph. So now we can use direct substitution, plug in 1 for x, and we get 3/2. So we could write a piecewise function that would make this x cubed minus 1 divided by x squared minus 1 continuous at x equals 1 because it is a removable discontinuity, and we defined the function at x equals 1 to be 3/2. We've replaced that point to make it continuous. Now note, there is another discontinuity at x equals -1 that cannot be removed. But do you notice here that if we used direct substitution, we would not get 0 over 0. We would get -2 over 0. That's not the indeterminate form. Therefore, there's not a removable discontinuity at that point. Since we're getting 2 divided by 0, it appears that there's going to be a vertical asymptote at x equals -1. And we're going to take a look at the graph. So here's the graph of x cubed minus 1 divided by x squared minus 1. We can see the vertical asymptote at x equals -1. And at x equals 1, there would be a little hole there in the graph of the original function. But what we did is we created a piecewise function, and filled in that hole. And we made it continuous at that point. But at x equals -1, we cannot make it continuous. And if we looked at the limit of x cubed minus 1 all over x squared minus 1 as x approaches -1, if we use direct substitution, we'd get -2 over 0. That's not the indeterminate form, therefore it's not a removable discontinuity. It's an asymptote. Evaluate arcsine of 1 minus the square root of x divided by 1 minus x as x approaches 1. We are going to use some of the limit laws we learned earlier to rewrite this. First of all, we'd have the arcsine, and we can take the limit inside the limit of 1 minus the square root of x all over 1 minus x as x approaches 1. If we use direct substitution for this limit, we can see we get 0 over 0. I'm going to use the factoring technique to try to solve this one. The denominator can be factored into 1 minus the square root of x times 1 plus the square root of x. And now we can reduce 1 minus the square root of x, and we can use direct substitution now. We would have the limit of 1 all over 1 plus the square root of x as x approaches 1. So we would get 1 all over 1 plus 1 is 2. So we have the arcsine of 1/2. Now if you recall your trigonometry, the arcsine of a number will equal an angle, and the arcsine is restricted from -90 to +90, or negative pi by 2 to pi by 2. So the sine of what angle equals 1/2? We know that the sine of 30 degrees equals 1/2, or if you were in radians, pi by 6. Since we want a real number value, we're going to use the radian measure. So we'd have pi by 6. Continuous functions can be added, subtracted, multiplied, divided, and multiplied by a constant, and the new function remains continuous. Composite functions of continuous functions are also continuous. So looking at these examples, here's the argument of the sine function x squared. So x squared, that is a continuous function. We've put it inside the sine function, so we have a composite function. X squared is a continuous function, sine is a continuous function, therefore the sine of x squared is a continuous function. Likewise for y equals the absolute value of cosine of x. Here's an important theorem. The following types of functions are continuous at every number in their domain. What's nice about this theorem is if we're given a problem and it asks us to find where is this function continuous, well, we could say this is a polynomial function, and polynomial functions are continuous at every number in their domain. We're finished. Likewise for all of the rest of these functions. If you have an inverse trigonometric function, you can just say inverse trig functions are continuous everywhere on their domain. The last concept, the intermediate value theorem. If a function is continuous between a and b, then it takes on every value between f of a and f of b. This can be shown easily with a graph. Here we have the graph of a function, and an important thing to remember when you're using the intermediate value theorem, you have to state that the function you're working with is continuous. Now we know, since we're working with a smooth continuous curve, this one appears to be continuous. So here's the value of a, here's the value of b, here's f of a, here's f of b. Now let's take, for instance, if f of a was 2 and f of b is 7, let's say. The intermediate value theorem states that this function must take on all y values between 2 and 7. I could find a value of x if I want to show that this is going through 6.8. I could find a value of x that I could plug into the function that would give me 6.8. It must take on every value from 2 to 7 on the interval a to b. Is there any real number exactly 1 less than its cube? Notice this problem is not asking us to find the value, but it's just simply asking, does one exist? Let's translate this into a mathematical sentence. That translates into x equals x cubed minus 1. Is there any real number, x, there's our x, that is exactly 1 less than its cube? And so on the right-hand side of the equation, we have x cubed minus 1, 1 less than its cube. Now, if we subtracted a x from both sides, we'd get x cubed minus x minus 1 equals 0. So if we can show this graph crosses the x-axis, which means it equals 0, then we've shown there is a number that's exactly 1 less than its cube. Now, let's use the intermediate value theorem to help us show this is true. We are working with a continuous function. X cubed minus x minus 1 is a polynomial, so it is continuous everywhere on its domain. Now, if we took f of 1, if you plugged in 1 to this function, you would see you get negative 1. If you looked at f of 2, you get 5. So that means this graph must cross the x-axis between 2 and 5. I'm sorry, between 1 and 2. Because we said when x equals 1, we get negative 1. When x equals 2, we get positive 5. So if this is a continuous function, it must go through the x-axis. Therefore, this has to be true at that value where it crosses the x-axis. So we have shown that there does exist a number that's 1 less than its cube using the intermediate value theorem. Now we could find the actual value by using a calculator. Let me get rid of that. And if you use your graphing calculator to graph y equals x cubed minus x minus 1, show that there is a root of the equation where it crosses your x between 1 and 2. You'd get approximately 1.3. We're going to use the intermediate value theorem. Now we're working with a polynomial. Polynomials are continuous everywhere. So if I can find a value that gives me a negative number and another value that gives me a positive number, it has to cross the x-axis between those two values. So if we looked at f of 1, if we plugged in 1 to the equation, we would get negative 1. And if we plugged in 2 to the function, we would get 12. Therefore, the results of the intermediate value theorem, and we can abbreviate intermediate value theorem, IVT. The intermediate value theorem states that since we're working with a continuous function, and I showed that f of 1 is a negative number, f of 2 is a positive number, so at 1 here we had a negative value, at 2 we had a positive value, so it must cross the x-axis between 1 and 2. So there has to be a root of this function between 1 and 2.